Hello everyone. Let's look into the final section of the physical design flow, which is parasitic extraction. So in a broader sense, it means that we have got this physical wires. So the parasitic extraction says us that each and every wire has got a finite resistance and capacitance, and we have to extract it and then provide it to the analysis tool. That's what parasitic extraction means in a broader sense. Okay, but the real problem lies in how do you represent this particular resistance and capacitances in a file format. Okay, so the format of this particular of the format, or the way you need to represent the resistance and capacitance, that's the key of parasitic extraction. In a broader sense, it looks very simple. You just need to extract resistance and capacitance, but from an analysis point of view, it needs to be the data needs to be structured in a specific format. It needs to be represented in a specific format. So let's look into one such a representation format, and that's called as the SPEF format. So let's bring it over here. We'll remove the netlist, and that's called as the SPEF format. It's called as standard parasitic exchange format. It's an IEEE 1481/1999. It's an IEEE format that is being used across tool vendors. So any tool vendor has to follow the IEEE format for the SPEF, so that there is some standard way to represent the resistance and capacitance that can be used by others as well. Okay, so that's the format, and we'll try to understand each and every parameter of this particular format in this particular section. So basically, if you have some resistance and capacitance, how will that look in a standard parasitic format? Let's try to look into those things in this section. Okay, because that's the key in parasitic extraction. Else there's nothing great about parasitic extraction, except that it has to be represented in a certain format. Okay, so let's bring up some section of the circuit. For example, let's look into this small section of the circuit where you have the D into as an input port, the buffer, and the flip-flops. Okay, and let's keep the remaining wires as it is. That doesn't matter to us. Okay, we'll look into how do we represent this small section in a SPEF format, and that can be propagated for each and every wire. That concept can be propagated, or it's valid for each and every representation of the wires. Okay, so for example, now this particular path, let's try to identify the path components. So it has got a D into, which is an input port. Okay, and if you try to look into the input port of, if you try to look into this particular input port, there are multiple things that is associated with this input port. For example, the first thing is the load capacitance. So if you see the load, this particular input port does see some load at this particular point, and that load capacitance, which is associated to D into, is represented in a SPEF way called as star L. So star L is an IEEE SPEF format to represent load of any input port or any input net or any net. Okay, so star L is the load, and wherever you see star L in your SPEF file, it represents the load of that particular corresponding input port or a net. Next, if you have it has got a coordinate. So this D into, if you plot this floor plan onto an XY axis, for example, if this is your Y axis and this is your X axis, D into will have certain coordinates, and things work, and the complete flow works on coordinate system. So this D into port will have certain X and Y coordinate. So if you see star C in front of any of the input ports or nets, that represents the coordinates of that input port or the net. Okay, next, when you try to dig in more of this input, the properties of the input port, you will come to know that it has got some driver. So there is some, if this particular box was a part of a big design, there would have been some driver which is sitting and sending some signals to D into port, and that has been getting inside this chip. So there is some driver which is sitting over here, and that if there is a driver, that driver is the type of the driver is represented by star D. So let's say if you see any input port with star D as, let's say, BUF buffer, it represents that there is a buffer which is driving the D into port. Okay, and again you have the waveform shape or the rise and the fall transition. So there is some waveform that is entering, or there is some transition or some signal that is entering into this chip through this particular port. Okay, and if there is so, then they will be represented by star S. So you will have two values for star S. One is for the rise transition and one is for the fall transition. So if you see any input port with the star S X ABC comma XYZ, it represents that the star that this particular input port is being fed by a signal with transition as with a rise transition of ABC and a fall transition of XYZ. Okay, so let's look at a sample example for the D into port itself. If you try to represent D into port in a SPEF format, it will look something like this. So the SPEF equivalent of D into is, let's say it is called as star ports. The star ports, whatever comes under star ports, it basically represent, these are all the input and output ports. In our case, it's D into, so we have this D into. The D into is an input port, so I over here will represent that D into is an input port. Okay, then star L will represent the load that the input port is seeing. So this particular input port sees a load of 0.05. So whether it's picofarad or femtofarad, we'll come to that in a bit from now. For now, it's we are using a unit of picofarad, but there is a way to tell the system that we are following certain unit system. So we will tell the system in a bit from now. For now, assume that this is a 0.5 picofarad or 50 femtofarads. Okay, and the slew value or the rise and the fall transition signal that the D into port is receiving are 100 picoseconds. And again, there is a time unit to it. So whether it's 100 picosecond or 100 nanosecond, that is again defined by some unit system that we need to follow in this SPEF, and there is a way to pass that information also in the SPEF format. We'll look into that in some time from now. For now, in order to represent the D into port, this is the way to do it. So we have under the star ports section, we have D into as an input port. I represents D into as an input port, and the star L represents that this D into input port sees a load of 50 femtofarads, and star S says that the D into input port is receiving a signal transition having a rise transition of 100 picosecond and a fall transition of 100 picosecond. That's what this says. Okay, and there is another way to represent the same thing. So for example, in this case, you have only one input port and one output port. Imagine there would have been a chip which has got like hundreds of input ports and hundreds of output ports, hundreds of nets, thousands, millions of nets. In that case, the file, in order to maintain the size of the file becomes really bulky to mention each and every net name. Rather than that, what we can do, we can map this to certain numbers. So for example, we have got an attribute in the SPEF format. It's called a star name underscore map, and we can map the D into port with some numbers. So for example, star 1 is mapped to D into. So for example, in the complete SPEF file, whenever you see star 1, that represents the port. And there will be millions of lines similar to star 1. For each and every net can be mapped to some numbers, and the idea for doing that is to reduce the SPEF file size, and we'll come to know in a bit from now how important how big the file becomes and how important it is to maintain the SPEF file size. Okay. So now in this case, we have just used the attribute name underscore map, and D into is being mapped to star 1. Okay, and now you use star ports section, and instead of D into, replace D into by star 1. So instead of 3 words, now you have, instead of 4 words, you have now only two. Instead of 4 letters, you have 2 letters, and that, and imagine the number of letters that can be reduced by using naming, by using mapping technique for all the nets present over here. The file size greatly reduces. Okay, so this and this are both the same. Oh, instead of D into, we are using *1. I remains I, which is an input port. *L remains *L, and *S remains *S. Okay, so that was one section of the, that is one section of this SPEF file which is being represented in this format. And let's take this particular thing out of the box and keep it in a file. Let's say this is our SPEF file, and this is one section of the SPEF file. Okay, next what we have to do is we have to take, let's say, this particular net and try to represent this net in a SPEF format. So since I'm already running out of time, let's try to bring this up, and let's try to bring the proper attributes of this particular net and represent in the SPEF format in the next video. Thank you.